Have you ever gazed up at the night sky, your eyes drawn to the twinkling stars scattered across the vast expanse, and wondered, where does it all end? Could there be an edge to this seemingly infinite tapestry we call the universe? The universe is a place of profound mysteries, a cosmic ocean of stars, galaxies and nebulae, all interwoven by the fabric of space and time. But perhaps the most captivating mystery of all is the question of its boundaries. Does the universe stretch out infinitely, or does it eventually come to an end? Join us now on this exhilarating journey as we venture to the very edge of our understanding, seeking answers to these fundamental questions about the cosmos and our place within it. Prepare to have your mind stretched, your imagination ignited, and your perspective forever altered as we explore the mind-boggling concept of the universe's edge. Imagine yourself at the center of an immense, expanding bubble. This bubble represents the observable universe, the portion of the cosmos we can perceive from Earth. Our planet, our solar system, even our galaxy, all reside within this cosmic bubble. But what lies beyond the edge of this bubble? The answer, as perplexing as it may seem, is that the universe extends far beyond what we can currently see. The edge of the observable universe is not a physical boundary, but rather a limit dictated by the finite speed of light and the universe's age. Think of it this way: when we observe distant galaxies, we are looking back in time. The light from these galaxies has been traveling for billions of years to reach us. The farthest we can see is the distance light has had to travel since the Big Bang, roughly 13.8 billion years ago. However, the universe hasn't remained static during this time. The universe is expanding, which means that the space between galaxies is constantly stretching. This expansion has profound implications for our understanding of the universe's edge. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery that revolutionized our understanding of the cosmos. The universe is expanding. Hubble observed that galaxies are moving away from us, and the farther away a galaxy is, the faster it is receding. This expansion isn't like the explosion of a bomb, where fragments are propelled outward from a central point. Instead, it's the fabric of space itself that is stretching, carrying galaxies along with it. Imagine dots on the surface of a balloon as it's inflated. As the balloon expands, the dots move farther apart, just like galaxies in our expanding universe. This expansion has a profound effect on our ability to perceive the universe. As space expands, it stretches the wavelength of light traveling through it, causing a phenomenon known as redshift. The farther away a galaxy is, the more its light is redshifted, eventually shifting beyond the visible spectrum and becoming invisible to us. This means that there are regions of the universe beyond the observable universe that we cannot currently see and may never be able to see due to the ever-increasing expansion of space. The light from these regions is simply moving away from us too quickly to ever reach our telescopes. So, if the observable universe isn't the edge, what lies beyond? The answer, shrouded in mystery and speculation, is a topic of intense debate among cosmologists. One possibility is that the universe extends infinitely in all directions, a boundless expanse teeming with galaxies, stars, and perhaps even forms of matter and energy we have yet to comprehend. Another possibility is that the universe is finite, but without a boundary or edge. Imagine a flat sheet of paper. If you could travel far enough in one direction, you would eventually reach the other side, not by crossing an edge, but by traversing the entire finite surface. Similarly, a finite universe could be curved in on itself, such that traveling in one direction would eventually lead you back to your starting point, much like circumnavigating the globe. In this scenario, there would be no outside to the universe, as it would encompass all of space and time. The true nature of the universe beyond our cosmic horizon remains one of the most profound and tantalizing questions in science. As we continue to explore the cosmos, developing new technologies and refining our understanding of fundamental physics, we may one day unlock the secrets of the universe's ultimate extent. Let's imagine for a moment that the universe isn't infinite, that it does have an edge, a boundary beyond which nothing exists. Would we ever be able to reach it, to peer beyond the veil of the cosmos and glimpse whatever lies beyond? The answer, unfortunately, is a resounding no. You see, the very nature of the universe's expansion makes reaching the edge, even if it exists, an impossible feat. It's not simply that the edge is incredibly far away, it's that the expansion of space itself is constantly pushing it farther and farther from our grasp. Imagine a swimmer trying to reach the horizon. No matter how hard they swim, how fast they propel themselves forward, the horizon always seems to remain the same distance away. This is because the Earth's curvature keeps pushing the horizon out of reach, just as the universe's expansion keeps pushing its edge beyond our grasp. Even if we could travel at the speed of light, the ultimate cosmic speed limit, we would still be unable to outrun the expansion of space. The edge of the universe, if it exists, is receding from us faster than the speed of light, ensuring that it will always remain beyond our reach. But what if the universe doesn't have an edge at all? What if instead of being finite, the universe extends infinitely in all directions, an endless expanse of cosmic wonders? This mind-boggling concept, while challenging to grasp, is entirely consistent with our current understanding of cosmology. To visualize an infinite universe, imagine a flat sheet of paper extending infinitely in all directions. No matter how far you travel on this sheet, you will never encounter an edge or boundary. Similarly, an infinite universe would have no center, no single point that could be considered its origin. Now imagine bending that flat sheet of paper into a sphere. The sphere, while finite in its surface area, still lacks an edge or boundary. An ant crawling on the surface of the sphere could travel in any direction indefinitely without ever encountering an obstacle. In a similar way, an infinite universe could be curved in on itself, creating a closed, boundless structure. This concept is known as a closed universe, and it's one of the possible geometries for the cosmos, according to Einstein's theory of general relativity. If the universe were finite and small enough, you might think we could see all the way around it, like looking across a room. However, the universe has a few tricks up its sleeve, one of which is the cosmic microwave background radiation, or CMB. This faint afterglow of the Big Bang permeates the entire universe and provides us with a glimpse of the early universe just a few 100,000 years after the Big Bang. The CMB is remarkably uniform in temperature, with only tiny fluctuations. These fluctuations, however, are incredibly important as they represent the seeds of the large-scale structures we observe in the universe today, such as galaxies and galaxy clusters. By studying the patterns in the CMB, cosmologists have been able to determine the geometry of the universe. The latest measurements suggest that the universe is very close to being flat, meaning that it extends infinitely in all directions. However, these measurements also have a margin of error, leaving open the possibility that the universe could be slightly curved either positively or negatively, which would have implications for its size and ultimate fate. For a moment, let's indulge in a thought experiment. Imagine a universe where the very fabric of space remains still, unyielding to the forces of expansion. In this static cosmos, the concept of an edge takes on a different meaning, a more tangible and perhaps even attainable boundary. Without the relentless stretching of space, the edge of the universe, if it exists, would no longer be a moving target. It would be a fixed point in the cosmic expanse, a tantalizing destination for intrepid space travelers seeking to reach the ultimate boundary. In this static universe, light from every corner of the cosmos would have ample time to traverse the vast distances, eventually reaching our telescopes. We would be able to observe the universe in its entirety, witnessing the birth and death of stars, the collisions of galaxies, and perhaps even the echoes of the Big Bang itself, all playing out across the canvas of the night sky. However, this static vision of the universe is merely a hypothetical construct, a thought experiment designed to highlight the profound implications of cosmic expansion. Our universe is far from static, its very essence defined by constant motion and evolution. The reality of our expanding universe presents us with a profound limitation, a cosmic horizon beyond which our current understanding of physics cannot penetrate. This horizon, located approximately 46 billion light-years from Earth in all directions, marks the boundary of the observable universe. It's important to understand that the cosmic horizon is not a physical barrier, but rather a limit imposed by the finite speed of light and the universe's expansion. As we gaze deeper into space, we are looking back in time, observing light that has traveled for billions of years to reach us. However, the expansion of space stretches the wavelength of light, causing it to redshift. Beyond the cosmic horizon, the expansion of space is so great that light from these distant regions is redshifted to the point where it becomes undetectable by our instruments. This means that there could be an untold number of galaxies, stars, and perhaps even entire civilizations beyond the cosmic horizon, hidden from our view by the vast gulf of space and time. Their light will simply never reach us, no matter how powerful our telescopes become. The concept of a cosmic horizon, a boundary beyond which we cannot see, ignites our imagination and fuels our insatiable curiosity about the true nature of the universe. What lies beyond this veil of the unknown? Are there other universes, perhaps governed by different laws of physics, existing parallel to our own? The idea of a multiverse, a vast collection of universes with potentially infinite variations, is a topic of intense debate and speculation among cosmologists. Some theories suggest that our universe might be just one of many bubbles that emerged from a primordial quantum foam, each bubble representing a unique universe with its own set of physical laws. Other theories propose that parallel universes could exist within higher dimensions, hidden from our perception, but potentially interacting with our own universe in subtle ways. The existence of such parallel universes would have profound implications for our understanding of reality, suggesting that our universe is just a small part of a much grander and more complex cosmic tapestry. While the concept of a multiverse remains highly speculative, it highlights the limits of our current knowledge and the vast potential for discovery that lies ahead. As we continue to explore the cosmos, pushing the boundaries of our understanding, we may one day unlock the secrets of the universe's ultimate extent and the nature of reality itself. Imagine a vast, flexible sheet stretched taut, representing the very fabric of our universe. This sheet is not merely a backdrop for cosmic events, but an active player in the grand cosmic drama. This is space-time. As described by Einstein's groundbreaking theory of general relativity, is the four-dimensional tapestry that weaves together the three dimensions of space with the ever-flowing dimension of time. It's not an empty stage, but a dynamic entity, warped and molded by the presence of matter and energy. Massive objects like stars and galaxies create depressions in space-time, much like heavy balls placed on a stretched sheet. These depressions dictate the movement of objects around them, a phenomenon we experience as gravity. The more massive the object, the deeper the depression, and the stronger its gravitational pull. Space-time, then, is not merely a concept, it's a fundamental aspect of the universe, an invisible scaffolding that underpins the very existence of everything we observe. It dictates the paths of planets around stars, the dance of galaxies within clusters, and even the trajectory of light itself. But what if we could reach out and touch this fabric of reality? What if we could somehow manipulate space-time, bending it to our will, or even tearing through its delicate structure? Such an endeavor, while seemingly the stuff of science fiction, takes us to the very edge of our current understanding of physics. Deep within the heart of our galaxy, and countless others scattered throughout the cosmos, lurk enigmatic objects of immense power and mystery, black holes. These celestial behemoths represent the ultimate triumph of gravity, regions where space-time is warped to its breaking point. Black holes form when massive stars collapse at the end of their lives, their cores imploding under their own immense gravity. The result is a singularity, a point of infinite density and zero volume, where the known laws of physics break down. Surrounding this singularity is an event horizon, a point of no return, beyond which nothing, not even light, can escape the black hole's relentless gravitational pull. At the event horizon, space-time is stretched and distorted to an extreme, like a piece of fabric pulled taut to its breaking point. It's here, at the very precipice of the unknown, that we encounter the possibility of tearing the fabric of space-time itself. While our current understanding of physics cannot fully describe what happens inside a black hole's singularity, some theories suggest that the immense gravitational forces could create wormholes, hypothetical tunnels that connect distant points in space-time. These wormholes, if they exist, could provide shortcuts through the vast expanse of the cosmos, allowing for travel across unimaginable distances, perhaps even to other universes. However, wormholes, as predicted by our current understanding of physics, would be incredibly unstable and fleeting, collapsing faster than the speed of light. Even if we could somehow stabilize a wormhole, the journey through it would be fraught with peril, as the intense gravitational forces and unknown physics at play could have unpredictable and potentially catastrophic consequences. The concept of wormholes has captured the imaginations of scientists and science fiction writers alike, offering the tantalizing possibility of bridging the vast distances between stars and galaxies, perhaps even allowing us to peer into other universes or dimensions. Imagine a sheet of paper folded in half with 2 points marked on opposite sides. A wormhole would be like a tunnel punched through the paper, connecting these 2 points and providing a shortcut through the intervening space. Similarly, a wormhole in space-time could connect distant regions of the universe or even different universes altogether. Theoretically, a wormhole could allow for faster-than-light travel, as the distance traveled through the wormhole itself could be much shorter than the distance between the 2 points in normal space. This could have profound implications for space exploration, potentially allowing us to reach distant stars and galaxies within a human lifetime. However, creating and maintaining a wormhole would require manipulating energy and matter on a scale far beyond our current technological capabilities. The immense gravitational forces involved would likely rip apart anything that attempted to enter the wormhole, and even the slightest disturbance could cause it to collapse, trapping anything inside. Despite the immense challenges and potential dangers, the concept of wormholes continues to fascinate and inspire, pushing the boundaries of our imagination and challenging us to explore the most extreme limits of physics. While the existence of wormholes remains purely theoretical, the possibility, however remote, of unlocking their secrets hints at a universe far stranger and more wondrous than we can currently comprehend. Our exploration of space has taken us from the vast cosmic horizons to the enigmatic depths of black holes, but now we venture into a realm even stranger and more counterintuitive, the quantum vacuum. Far from being an empty void, the quantum vacuum is a seething sea of virtual particles flickering in and out of existence with a frenetic energy that belies its apparent emptiness. These virtual particles, predicted by the laws of quantum mechanics, are not like the familiar particles that make up atoms and matter. They exist in a state of quantum superposition, simultaneously both existing and not existing, their presence a fleeting whisper in the fabric of space-time. Imagine a vast, dark ocean, its surface seemingly calm and undisturbed. Yet beneath the surface, a maelstrom of activity churns unseen. Countless tiny bubbles, formed by the random motion of water molecules, constantly pop into existence, only to vanish just as quickly. Their fleeting lives a testament to the inherent energy of the system. The quantum vacuum operates in a similar fashion. Virtual particle pairs, consisting of a particle and its antiparticle, spontaneously arise from the vacuum, their existence governed by Heisenberg's uncertainty principle, which allows for brief violations of energy conservation at extremely small scales. These virtual particles, however, are incredibly short-lived, annihilating each other almost immediately after their creation, returning their borrowed energy to the vacuum. The quantum vacuum, far from being a static and inert backdrop, is a dynamic entity, a constant dance of creation and annihilation, where particles flicker in and out of existence like fireflies on a summer night. This ceaseless activity has profound implications for our understanding of space itself. One of the most intriguing consequences of the quantum vacuum is the Casimir effect, a phenomenon predicted by Dutch physicist Hendrik Casimir in 1948. The Casimir effect arises from the interaction of virtual particles with two closely spaced, uncharged conducting plates. Imagine placing two mirrors facing each other in a vacuum. The mirrors, due to their conductive nature, restrict the types of virtual particles that can exist between them, creating a slight pressure difference between the space inside the mirrors and the space outside. This pressure difference, though incredibly small, has been experimentally verified and provides compelling evidence for the existence of virtual particles and the dynamic nature of the quantum vacuum. The Casimir effect highlights a profound point. The quantum vacuum is not merely a theoretical construct, but a tangible entity with measurable effects on the physical world. Its influence can be seen in a range of phenomena, from the behavior of atoms to the expansion of the universe itself. Our exploration of the quantum vacuum has brought us face to face with the limits of our current understanding of the universe. The laws of quantum mechanics, which govern the behavior of matter and energy at the smallest scales, seem at odds with Einstein's theory of general relativity, which describes the force of gravity and the large-scale structure of the universe. Quantum mechanics describes the universe as inherently probabilistic, where particles exist in a haze of uncertainty until measured. General relativity, on the other hand, depicts a deterministic universe where the fabric of space-time curves in response to the presence of matter and energy, dictating the paths of objects with unwavering certainty. This fundamental clash between our two most successful theories of physics suggests that a deeper, more fundamental theory is needed, a theory that can reconcile the quantum world with the realm of gravity, a theory of everything. Many physicists believe that such a theory would require a radical shift in our understanding of space and time. Perhaps, as some theories suggest, space and time are not fundamental aspects of reality but emergent properties, arising from a deeper level of reality that we have yet to comprehend. Imagine a mosaic, its intricate patterns and vibrant colors emerging from the arrangement of countless tiny tiles. Space and time, in this analogy, would be like the patterns in the mosaic, their apparent continuity and smoothness an illusion created by the underlying discrete nature of reality. The quest for a unified theory of everything is one of the most ambitious and challenging endeavors in modern physics. A journey that takes us to the very edge of human knowledge and forces us to confront the deepest mysteries of the cosmos. As we conclude our journey to the edge of the universe, we find ourselves standing at the precipice of the unknown, humbled by the vastness of the cosmos and the profound mysteries it holds. The question of whether the universe has an edge, a boundary beyond which nothing exists, remains one of the most tantalizing and elusive in all of science. Perhaps the universe stretches out infinitely, a boundless expanse teeming with galaxies, stars, and wonders yet to be imagined. Or perhaps it curves back on itself, finite yet unbounded, a cosmic sphere with neither beginning nor end. The answer eludes us, hidden behind the veil of the cosmic horizon, a boundary imposed by the finite speed of light and the relentless expansion of space itself. Yet even as we grapple with these profound questions, we are filled with a sense of awe and wonder. The universe, in its immensity and complexity, speaks to something far grander than ourselves, a cosmic tapestry woven from the threads of space, time, matter, and energy. And so we continue to explore, to probe the depths of space with our telescopes, to unravel the secrets of the quantum world with our experiments, and to push the boundaries of human understanding with our theories. The journey to the edge of the universe is a journey without end, a testament to the boundless capacity of the human spirit to explore, to question, and to marvel at the wonders of the cosmos.